So this is our second video for slope fields, and hopefully you had a chance to finish up this example and just drawing a dash or a tick mark in the direction of the slope. And again, just as a review, this particular function as a differential equation only depended on y. It was every component was y squared. So when I looked at, for example, this point right here, 0, 2, its y value was 2. So it's 2 squared is 4. So I tried to draw something that had a slope of 4, which is steeper than a slope of 1, and not quite as steep as something up here, which was 0, 3. And that would have a slope of 9 because 3 squared is 9. So if you take a look, each row, because each row, so like this row all had the same y values, and then the row above it had the same y value. So every row that has the same set of y values would have the same slope or have the same tick mark. So then, and the same thing down to negatives. And when you square the negative, it becomes positive. So you should get something that looks like this. And then it says, draw a particular solution goes through -1, 1. So I went ahead and labeled and drew -1, 1. And when it asks you to draw a solution, you just sort of have to kind of follow the trend lines, right? So it clearly, as it goes here, it begins to increase. Oops, sorry. So it begins to increase. And, it's not perfect. And then as it comes down, it sort of flattens out. And then again begins to decrease. So let me try to make that just a little bit better for you. So we have this slope here, and it's increasing, and then it begins to like kind of taper off, and then it begins to decrease like that. So again, it's as long as you go through that point, and as long as the curve goes in the general shape of your slope field, you'll be fine. And this is, again, I should have mentioned this in the first video. It's just an introduction to slope fields. It's introduction to this idea of differential equations. And then we'll start, as we move through this chapter and into the next chapter, start looking at it maybe with, at more and more complicated functions. But for now, we're just sort of introducing what is this idea of a slope field. A slope field could represent a whole family of antiderivatives, and it can represent visually what that differential equation is going to look like. Okay, now the next one, it says here's another differential equation, but this particular one is dependent both on the x and the y coordinate. And so I've got to be really careful, and it does become meticulous that each of the components are going to contribute to the slope field. So for example, and also it says like y can't be equal to 0 because I don't want to divide by 0. So any place where there's y's are 0, which is basically the x-axis, right? All of this is y equals 0. I'm not going to draw anything because it says y does not equal 0. So the first point I might go to is like 1, 1. And so for 1, 1, I would put in the x is 1, the y is 1, and that would be 1 over 1, but make it negative. So it's going to have like a -1 slope. And I kind of think, well, wait a minute, like 2, 2, even though I'm saying it, it's not writing. So 2, 2 would also have a slope of -1, right? Because 2 divided by 2 is 1, but make it negative. So this this diagonal working out, and this is 3, 3 would have a slope of -1. And even down here at -1, 1 would have a slope of -1. -2, 2 would have a slope of -1. I'm just kind of, again, trying to find out, and this one right here would have a slope of -1. Just trying to find out maybe a pattern that would help me go through this a little bit more efficiently. Now, when I get out to here to 2, 1, so I look at the differential equation, and it's -x over y. So -2 over 1. So it's like a slope of -2. So it's a little bit steeper than that one. And then this is 3, 1. Put it into the equation. It'd have a slope of -3 over 1. So even steeper. And if I put this point here, which is 0, 1, it would be 0 over 1, which is 0. So it's a slope of 0 at this point. And actually, I can go up that vertical y-axis because all of the x components, 0, 2, 0, 3, they all would have a 0 slope. Same thing down here, here, and I think I'm scrolling down here, missing one more here. Okay, so those all have a 0 slope, and so then maybe I will go up here to 1, 2. So again, it's negative x over y, so it's negative 1 over 2, so it's negative half. So it's not quite as steep as, this is negative 1, so negative half, so not quite as steep. There was negative 1, and if you put this 3, 2 here, you get negative 3 over 2, so a little bit steeper. Excuse me. There it is. Okay, and then again, kind of finishing up the quadrant. This is 1, 3, so this would have a slope of 1/3. This would have a slope of, negative 1/3. This would have a slope of negative 2/3. A little steeper. This is a slope of negative 3/3. So the further you go, it gets steeper and steeper in the negative direction. Well, if I look over here to this point, it's going to give me basically it's the mirror reflection, because at negative 1, 1, now all of a sudden negative 1 over 1 becomes a positive 1. So it's going to go in this direction. And if I go up the diagonal, I get that slash mark. And I go up this, right? All of these points, when I put it into my differential equation and I look at the negative x over the y component, they're all going to give me a slope of 1. And as I start to fill this in, I kind of start to notice a pattern. Like it's almost appearing to be circular to me. So again, going over negative 1 up 2, this would have a slope of positive 1/2. So not quite as steep as this. And then as you go out, it gets a little bit more steep. And then again, this up here would be a slope of 1/3. This would be 2/3. And that would be 3/3 or 1. So, once you start to find the pattern, again, it doesn't have to be an exact, precise slope. It's all kind of relative to your scale, but you get to kind of get this picture. And again, it sort of looks circular, and then that's exactly what it should look like. It should start to look like a bunch of concentric circles, or circles that share the same radius. So again, I'm just kind of ballparking the slope values based on the pattern that I found. Okay, and then, sorry, hold on one more second here. There we go. So again, I hope I see the circular path. And when it says, draw the point that goes through 2, 2, which is that point right there. So 2, 2, I want to draw a function that goes through that point. So kind of like in the circular mode. But I do have to be careful that y can't be 0. So when I come through here, I have to be really, really careful not to go through 0. So I put an open dot and an open dot. So since I can't be 0 and I want to draw this as a smooth connected curve, that's all I can do. So half of the solution would be above that, this 2, 2. And that's why I gave example B. So if you look at example 3B, it's the exact same slope field, but now it says we'll go through 2, negative 2. Well, 2, negative 2 exists down here. Oh, sorry, exists down here. I thought I picked red. Try one more time. Orange. There we go. Exists down there. So again, being circular, but realizing that I can't cross that because it says y can't equal 0. So pretend that's a circle. All right. So in looking at this video and kind of looking at the big picture of our slope fields, it's sort of an introduction. So look at each of the lattice points, look at the x, look at the y, and if your differential equation depends on both, then you do the operation to represent what the slope is at that particular point. And like I said, as we move through this chapter and as we move through next chapter, we'll again start to look at more and more sophisticated slope fields and use them to represent a differential equation that we'll eventually solve.